speaker tonight will be Andrea, and he will talk about how to verify Rust. You gave a talk at Rustfest Zurich in 2017.
That's right.
Yeah, so this is the second talk, I think, for Rust in Zurich?
In Zurich, probably, yeah. That sounds right, yeah.
Nice. So very happy to have him back. Little admin info, we expect a 45-minute-ish talk with questions, so you should all make trains at, let's say, 9:15. It takes 15 minutes to walk down to main station. If you have to leave early, just take the rear exit. Questions in between or afterwards?
Sure, no, totally, yeah. Feel free to interrupt.
Okay, just wave at me and then I will wave at Gary and he will bring you the mic. All right, let's start.
All right.
Thank you.
Thanks a lot for the intro and thanks for inviting. All right, so this talk is a bit more academic, maybe. So the topic is formal verification, so using kind of mathematical methods to prove that software is correct. And I'm going to talk about the tool we've been building. It's called Verus, which is a tool to verify Rust, and specifically verify Rust in the domain of system software, so operating systems, file system, things like that. So instead of trying to explain what verification is, I'm just going to jump into an example. Not this example. And so, you're writing your very simple max function here. Obviously, this is a stand-in of something hopefully a bit more complicated. And what you might do is, try and write a test for it. I'm keeping things extremely simple for the purpose of this. So I kind of just writing our own RNS to test this program. So we have a max function. We call it with certain arguments and check that the result is the one we expect. So if we run this program, it passes. Right? We wrote a test, it passes. We're happy. And I imagine that maybe some of you have already spotted the problem. The problem here is obviously that there's a bug, but also that the test case I wrote was insufficient. It was testing a very specific case that didn't catch the edge case, which is now huge for this example. But you can imagine, you can think about some cases in which you maybe didn't think about the test case that could have caught the issue. So, you could go and write another test and run it. And now, finally, we get the test failing because we swapped B and A over here. Right? So you can continue doing this. And that's how test-driven development has been working. And it works very well. One needs to be attentive in writing the tests that will catch edge cases or unexpected behavior. So here, the way I wrote test tree is a bit different. Instead of writing the return value that we expect exactly, I wrote the property I want the return value to have. So I'm saying the return value here should be either of the two arguments and should be the greater one of the two. If you've looked at property-based testing tools, that's something maybe it's already familiar with you, that you're already familiar with. So obviously, if I run the test again, now we're failing the assertion over here because we're now returning the right one. And I can fix the bug, and we're going to get the test passing, hopefully. Right. So the point I wanted to make here is you have to write this test, which tests kind of various points in the input space of this function, but you never know really that you've caught all the possible issues and bugs, and because you can't possibly know that you tested for all of the cases. So we're gonna now move into, so what I've been doing so far is just compiling with Rust-C. We're now gonna move using our tool, Verus. I'm gonna introduce it more later, but just bear with me for now. Just trust that this is something that exists, that I can run with the command Verus. And what I did here was take the max function from before, and then write an assertion. And this, as you can see here, it doesn't have the bang. It's a bit of a different syntactic construct. But I'm keeping the property that we wanted. Right? We want to say that that property is valid for the return value. And the error message we get from Verus is different. It's not a panic. We actually never run the code here. What we got here is two messages that say that this assertion failed. But Verus doesn't run the code. What Verus does is it statically checks every possible way to that this program could run. and checks whether these assertions are true in every possible case. Now, you're going to say, well, this is not going to work because this function is bugged. And I'm going to actually take the opportunity here for a second to introduce you to another concept in Verus, which is, despite me fixing the function right now, the tool is still not believing me. It's still telling me, well, these assertions are not true. The reason for that is that Verus, for various reasons, is modular. So it requires you to provide a specification for every function that you're trying to verify. And so what I did here was just to move those assertions into this ensures clause. And we're saying for this function, we want the return value to be either of the inputs and the greater of the two ones. So now, if I run Verus on this program, we get a new error message which says, failed this post condition here. And it's pointing out to exactly where the problem is. And that's happening at the end of the function body. But there's only one return here, so this is easy. So as you can imagine, we can go ahead and fix this, run it again, and now finally, Verus is happy with our program. It's saying the function is verified. So interestingly, once we have done this, conceptually, we don't need to write any tests anymore. Verus has just proven that for every possible A and B that you could pass to this function, these ensures clauses will hold. So we know that there isn't a possible input that would break the behavior of this function. Obviously, this is fairly trivial. You can imagine a more complicated program. Also, feel free to stop me if anything is unclear, or if you're like, what's that? Or if you want me to try something, please ask. I'm happy to try things out. Things might break, but that's the fun of it. So cool. So this is the verification. The promise of verification is this mathematical guarantee, this static guarantee that conceptually we've tested the function for every possible input, or tested the program for every possible input. Cool. So why Verus? Why am I talking to you about this tool and why we've been developing it? The context is that of all of the people on the first slide that you saw, a lot of them have been thinking about verifying system software as a way to have strong correctness guarantees. This is kind of the same goal as testing, but hopefully stronger. And as usual, like avoiding data loss and availability of bad consequences. But also, if we want to be able to use these techniques in the real world, we need to be able to use the verification process as part of regular development. We need to be able to build up the program while we verify it, and then keep this verification going. And also, once we've constructed the program, we need to be able to maintain the artifact and maintain the proofs that we will see will be necessary sometimes. So why Verus again? Again, we're looking at languages that we want to use for verifying system software. And if you're not familiar with the area, there is more and more interest in space. And this is moving in different ways from academia to industry. There's now verified projects and teams in various companies, but there's a spectrum of things you could use, and there's things that are easy to verify because they're more like math, and we are going to do math to try and improve properties of our programs. And there are things like closer to computers, so like whose code is closer to what you end up running on the actual computer, which is something that systems people often want. Like they want the control. They don't want to write sometimes a functional program because they don't have enough control. So Rust has this very interesting property of being on this side of the spectrum, zero-cost abstractions, efficiency, predictability. It's imperative, no garbage collections, all the good things that you want from a systems language, but also happens to be closer to that side of the spectrum. So it's in some ways a functional programming language, and has things that functional programming languages have had for a long time, such as algebraic data types, pattern matching, and restricted side effects. So we think of Rust as a very good language for this. And to reinforce this, and I'm not going to belabor the point, you're probably familiar, Rust enforces single ownership by default using what's called the Rust linear type system or affine type system, depending on your interpretation. And the demonstration here is just a tree data structure. We have a left and a right node at each node. And what we're going to try and do here is to assign the right child of left to also be the left child of right, which is clearly illegal, and Rust would reject this, right? So we have this guarantee that everything is owned uniquely. So again, this is why we like Rust for this goal. Rust linear type system tracks ownership and prevents what's called aliased mutable references, which means that what we get from Rust regularly is data races and user tree, all the nice properties you're familiar with. But in addition, we have noticed that aliasing is a challenge when doing functional verification, so the kind of technique to do development as I've shown before. And when you do functional verification of imperative code, it's often required that you need to think about what the data on the heap looks like and what pointers could potentially change which parts of the heap. And that's really difficult if you don't have the restrictions that Rust imposes. So the idea here is to rely on Rust linear type system instead. And here, we were not the first one to think about this, and there are some folks on this list in this room. Folks at ETH have realized this a few years back and started on a tool called Prusty that leverages these properties of the Rust type system to facilitate verification. We are going to take the similar idea, but taking a bit of a different direction. So again, this should be obvious. Rust prevents alias mutable references. And here I'm going to start with an example that goes into why it's useful for verification. So we have this structure, struct account as a balance. We have a function transfer that takes two accounts, source and destination, and an amount to transfer between them. So these are unique mutable references, as you know. And the ensures here, which says the balances change as they're supposed to, are only true if the origin and the destination are not aliased. So just to clarify, if we tried to call this function like this would be legal in a language like Java, for example, then the result would not be accounts that satisfy that property, because we are taking away and putting back money into the same account, but not in the right way to end up with the same result. And the problem here is that those two mutable references are aliased. So obviously Rust catches this problem, and because it does, then we can rely on this to say, well, then that ensures that property that we wanted to prove is actually true. Cool. Making sense so far? Cool, great. All right, so that's why Rust. Now, why Verus? So again, the goal is to make verification, formal verification practical for writing system software. And we started with some of the folks on the first slide using a tool called Daphne, which is a kind of C#-alike with integrated verification tools. And then, because we encountered all of these issues thinking about how to reason about aliasing when writing proofs in Daphne, we've integrated a linear type system into Daphne. So it kind of made Daphne look a little bit more like Rust. It was a fairly straightforward linear type system, but it indicated that that would have improved verification experience significantly. And so we started to think, well, we're trying to make Daphne look like Rust. Why not try to make Rust look like Daphne, which is a tool that we really liked in terms of the feature it provides for verification. I unfortunately can't really talk about more Daphne here, but you can look it up. It's a really interesting language. So that's how Verus came to be. Verus is our SMT-based intrinsic verification tool of safe Rust code. There's a few caveats. I'm going to get to all of them. Also, there's words that maybe you've not seen before. What does intrinsic verification mean? That's actually something that I was already talking about earlier, which is if we go back to our example and we try to verify it, you may know what to expect. You may know what may happen here. We haven't provided a specification for the transfer function, and so Verus can't really tell what's going to happen when we call transfer here. And also Verus is worried about the fact that we might overflow here and there. So Verus is also checking that no panics will happen. And the way we fix this, to start, is by adding what's called a precondition. So we're going to say the original balance before we call the function, this is what old overage says, should be greater than the amount. We shouldn't be able to withdraw more money than there is available in the account. And also, if we are depositing into the destination account, we shouldn't overflow U64 max. Now, if we run Verus again here, we notice that the two first errors, the two possible arithmetic underflow and overflows, are gone, because now Verus looks just at the body of this function and says, well, if we know these two things, then these two cannot possibly overflow. Yeah?
So in your second check, you have a strict inequality with max. Is that a restriction, or could you write
That's a good point.
less than or equal?
Yeah, no, I think it was a typo. Well spotted. Yes. Excellent question, by the way. Who verifies the verifier is a very good question. Doesn't fit in this talk.
Your transfer function has the exec keyword. What does that mean?
Great question. So we're going to get to that in a few minutes, but I can mention now that exec means that this function is something that we intend to execute. So it's program code that we intend to actually compile and execute. There's going to be other code that we don't intend to compile and execute, but I'll get to that in a second. And while I'm talking about this, you may have noticed that the syntax looks different. For example, this is not legal Rust. So what's happened here is we worked, and mainly Chris Oblitzel and Microsoft worked on this Verus macro, which you pass essentially the entire program into, or entire file into, and does a syntax transformation so that we get to use syntax that is more comfortable for using the tool for verification, but also still allows us to use the regular unmodified Rust compiler behind the scenes. So this is the unmodified Rust compiler, but with a custom driver. We get to have nice syntax, or the syntax we want, and the syntax we have learned to like from previous experiences using this macro. So you'll see Verus bang everywhere. Cool. So now we were saying that these two assertions down here are still failing, even though they should pass. And what we can do to fix that is make sure that we modularly describe what the transfer function does, because Verus is only going to rely on the specification to determine what happens when we call the function. And then we're just going to verify the two functions separately. So if we make that change and add the ensures and say, like, this is the behavior we expect, now Verus can verify the program. And I want to stress once again that we're not running the program. In fact, there's a joke in verification that people essentially never run their programs except like 2 days before the deadline, if you're in academia. But we still get, so in theory, if Verus is correct, there's no way that this program will go wrong. And so in some ways, you wouldn't need to write any tests. There are caveats to this, obviously. Great. So that's intrinsic verification. So a whole logic specification is a description of what happens before and after you call a function, for example. I said SMT-based as well, which is one of the possible techniques you can do verification of software. There's more manual techniques where you kind of write the proof steps by hand. But as you can see here, this program, albeit simple, verifies automatically. And the way we do this is by leveraging an SMT solver. So you may be familiar with SAT, which is Boolean satisfiability, which means you have an expression, and you're asking yourself, there exists an assignment of x and y such that that expression is true. And you could do this by hand, or you could grab Z3, which is a very powerful and often used SMT solver. And Z3 will tell you this expression is true if, for example, x is false and y is true. You can try. But what we're going to do actually is go and look at that program and actually run Z3 on it, so you get an idea of what it looks like. So what I did here is just write that expression from before, from the slide, in syntax that Z3 understands. And it's kind of this Lisp-like syntax. And then what I'm saying is check sat, which means does an assignment exist? And we're getting the response sat, yes, there is. And get model means tell me what that assignment, what one of those assignments could be. And here it's saying that y is true and x is false, which is what we expected from before. Cool. So there's an extension to SAT, which is what Z3 implements, which is SMT, satisfiability modulo theories, meaning that we're going to generalize SAT to formulas that include other theories, so real numbers, integers, data structures, and quantifiers, which turn out to be very useful when doing program verification. So for example, here we're going to say, we could say that for all a and b, a times b equals b times a, and we should be able to prove that. So in SMT-based verification, what we do is we start from the program. So here I'm going to try to explain to you in 2 minutes how Verus works at a very, very high level. So we're going to start with the program, and we initially wrote this test by hand, right? But what I've been saying is, we don't really want to pick two x and y's. We want to say what happens for any possible a and b, which we define by the ensures clause. And now what we're going to do is encode things like this. So what we want to prove is that for all a and b's, the max of a and b is a or b. So it's one of the two initial values. This is just kind of a logic encoding of this expression, and that it's greater than both, right? So what we're going to do is just turn that for all into a not exist not, which is a valid transformation. And Z3 is excellent at figuring out this exist part. So we essentially use Z3 kind of the other way around. We're asking it, can you prove that such an assignment does not exist? And if it can prove it, then it must be that for all a and b, that expression is true. And so if Z3 says sat or unknown, so there exists an assignment of variables that falsifies what we were trying to prove, then we failed. And if it says unsat, it means that Z3 can prove that there is no assignment to A and B that could falsify our postcondition. So we know that for every possible A and B, that's true. And if we're in SMT with all of the theories that we're talking about, we are in the realm of undecidability. So Z3 will encounter programs that it will just spin on forever. And that's a fundamental result in computer science. And we can't do anything about it. In general, in practice, we can actually prove a lot of useful programs, but there is this issue that sometimes Z3 just goes off and spins and never returns. And we need to figure out how to kind of deal with that. All right, so when using a tool like SMT, we get these automatic proofs that we were seeing before for free, at least at this level of complexity. That comes with the fact that we need to make sure to use this Z3 tool properly to extract as much performance out of this. If you're seeing that it takes us a very short time to get a response, but that's a very explicit design goal for Verus of getting a verification result back quickly in an amount of time that resembles how it would look like to just cargo check something, right? It takes longer for more complex functions, sometimes significantly longer, but that's very much our focus. And we achieve this by prioritizing efficient encoding to SMT queries, so the way we encode the program in Verus. And here, I think it's interesting to actually look at almost what the verification query that we pass to Z3 looks like for this program. So I did a tiny bit of editing here to just simplify things a bit. There is a bunch of prelude that I'm not going to talk about here. Just ignore this. It's fine. It's the same for. It's almost the same for every function. But I didn't want to be dishonest and delete a bunch of stuff. So this is not exactly the spin. I think I deleted 7 or 8 lines that are not critical for doing verification here. But this is the encoding basically in Z3 of our max function. So we are saying, see the not from before? We were proving that exists not something. And so that's exactly where it shows up. Our assumption is how the function looks like. So we're doing, if A greater than B, B A. And then what we're trying to prove is the postcondition from before. And we can just run Z3 on this. And if I write it correctly, we're getting unknown here, which means Verus cannot prove that the program is wrong. It also cannot prove that the program is correct. It's saying, and this is incompleteness, so meaning that Verus is not able to determine all the time which one of the two is the case, and this is, or rather Z3 in this case. However, we generally just treat unknown as a verification failure. We're just telling the user, we would be putting up to the user that message saying that assertion fails or that postcondition fails, and then the user has to come back and give us a bit more information to prove their program. Okay, so now this is unknown because it's a simple program that we expect Z3 to probably verify correctly, automatically, but the program is wrong because it's the same bug as before. So I'm just gonna, fix stuff so this kind of is the equivalent of fixing the function definition, and now we're getting unsat. And as a reminder, unsat means proof. So we've just proven that for every possible assignment to A and B, that program will always return something that satisfies our specification. Cool. So I've shown you smaller examples so far. I want to get once into what it looks like to verify something a bit more complex. And the example here is the iterative implementation of Fibonacci. So what we're doing here is just wrote the code, the executable code that we want. Exec is back here again because that's the code we actually want to execute. However, we need to be able to say what correct means in this context. And what we're going to try to do is say, well, we need to make sure for this function, we'll need to make sure that the return value, in fact, fits into a U64. Otherwise, we're not going to be able to return it. So we need to call it with an end for which Fibo will fit. And the ensure says the result is the Fibo of that number. But what does that mean? Well, in Verus, we have this other part of the language, which is essentially a functional language, functional mathematical language, which now is marked spec, that lets us describe the intended behavior of the program in a more abstract mathematical way. So this is the definition of Fibo that you would expect mathematically, and then Fibo fits U64 is just that. So let me run Verus on eFibo1. And what we're saying is, and Verus is saying, okay, not quite. This postcondition we cannot prove, and this might overflow. So here is where we have specified the function fully, we think, but SMT, the Z3 is behaving in such a way to avoid spinning off uncontrollably, and so it holds back in trying out potential proofs, and so we need to guide it a little bit. And the way we do that is by writing proof functions. So here, I'm not going to go into how we got here, but we're going to say we're going to need to know as a theorem that Fibonacci is monotonic, and in Verus a theorem is just a function with the keyword proof in front. And this is saying for I less than j, then Fibo of I is less or equal to Fibo of j. And we need to also prove that this function terminates, but that doesn't really matter here. I'm not going to get into how the proof exactly works. The fact that we are calling itself, if you remember proof by induction, that's exactly what we're doing explicitly. We are using knowledge about in inductive cases to prove this current case. And but again, I'm not going to go into exactly the details of the proof. And if we try and run Verus on this, so because we don't get an error, Verus actually can prove the Fibo is monotonic lemma. We just aren't using it yet. The way we get to use it is first we need to add an invariant. So whenever there's a loop, Verus will not actually infer some of the, or in fact all of the invariants that need to remain true for the loop to prove the postcondition. So we have to explicitly say this is the loop invariant. And then the other thing we need to do is to add this proof call that says here we need to prove, we need to use the knowledge that Fibo is monotonic for I and n, in this case, to support that this will not overflow. And there's a few hidden steps that Z3 does for us. So now, hopefully, if we run it on 4, we get a proof.
I have a question.
Yep.
So, I lost it. So the question was, how do you handle the bidirectional type system? But we don't have to explicitly type all the things, so we have let something. How do you handle?
Oh, you mean like type inference?
Yeah, type inference. Yeah.
Okay. We just do whatever Rust does. So all of this code gets passed on to after transformation. It actually doesn't look that different after transformation. Just looks like Rust, and we just rely on the Rust type checker, which is one of the big benefits of building a tool on top of Rust, is that we have access to all of that type system and all of those features from the type system. Okay. There are details in which we need to be very careful about the assumptions that are baked into the type system by Rust, and how we expose those assumptions, and how we treat, how you write your code so that those assumptions are upheld, and so.
So you use the high-level intermediate language, I assume.
Oh, great. So like how technically. So yeah, the different tools do different things. What we do is we take HIR and use that to generate the queries. Like there's a few layers of transformation, but basically we start from there. And then we at some point run the borrow checker. I'm going to get to exactly the fact that we don't always run the borrow checker with
all right, thank you.
yeah, thanks. Great question. So great. So this is, this Fibonacci function is now verified for any n that fits into U64 to actually compute Fibo. Cool. So this is all of the code in that proof, and I'm gonna highlight some of it and getting back to your question before. So this is exec code mostly. This is the code we actually want to run. This is proof code, so it's code that we used to explain to Verus and to Z3 why our program is correct. And this is spec code, so this is how this high-level mathematical language, kind of function language, in fact, this allows mutation, for example, that lets us specify what our program should do and lets us talk about some properties of the program. What's important here is that spec and proof mode code are ghost. Ghost meaning that all of this code will not appear in the final binary. It's only there for us to express what the program should do and to prove it correct. Great. So the interesting thing in Verus is that we treat, this is not quite exactly accurate, but it's I think a decent approximation, which is that we have 3 modes of code that we've seen, and we only type check spec code. We don't borrow check it. Which means that you actually can violate some of Rust's restrictions on aliasing in spec mode code, but that's sound because spec mode code is just a functional language. Proof mode code is treated as regular Rust, but we erase it before we get to compilation, and so that lets us express some proofs, and I'm going to show you a quick example in a second. And then exec mode code is just regular Rust program. We want to run that program. We're just going to compile it. Borrow check it first, then compile it. OK, so as mentioned, the Rust type system, something Verus relies on for its correctness. We do rely on the fact that Verus guarantees that for runtime values, there will not be alias mutable pointers, multiple references. But Verus also allows us going beyond what Rust supports, and hopefully without any UB and any unsafe in the kind of regular Rust sense. It's always terrifying to say a sentence like this with Ralph in the room, who just gave the talk from before, because there are a lot of details in getting things like this right, and this is a work in progress. So there may be still areas in which we have missed some soundness guarantees. We'll try to be very careful about soundness and only add features to Verus that will be sound, but the safety properties around code of this kind are complex, as discussed by Ralph earlier. And so Rust allows unsafe to break out of linearity. You get to do aliasing in there if you do it right. And Verus allows access to some other set of primitives that we wrote that are like pointers, the raw pointers, for example, that let us interact with these normally unsafe features in a safe way because the verifier is checking some of the assumptions. And here's an example. This is a bit involved, so I'm just going to try and go over the concepts. But what's happening here is we have a transfer permission function is just saying this is some ghost state that we use to describe the program that we're going to transfer away. Store copy of pointer just stores a copy of the pointer we pass it to. So think of PPTR as just a star-mute U64, but our version that's conditionally safe. And things like PPTR put is like assigning to 5, but there is this additional argument here, which I'll get to in a second, and then take is essentially like PPTR assigned to null. So what we are saying here is we're going to allocate a new pointer. It's going to point to nothing. Then we're going to give a copy of that pointer to somebody else. The pointer is just copyable. That's fine. We know that it doesn't contain anything. Then we're going to store a value of 5, and that should be worrying to you. We just gave a copy of to somebody else. That somebody else may spawn a thread and go and write into it. That's not great. That could be a data race, and that could be undefined behavior. However, we get to do this safely here because we have this tracked permission, which is a ghost, is some abstract representation of the fact that we can access the pointer, and that's treated like a regular Rust type, so linearly, so you don't get to alias it. And because we are still holding on to the permission, then we know that we are the only ones who would possibly be doing this operation at this point. And then once we do that, then we know that the contained value is 5. Then we try to transfer the permission elsewhere, because with some more complex proof around it, which I'm not going to be able to show, we're going to say somebody else now gets to write here. But this is totally a ghost operation, so it's not going to appear in the program code at all. And then we try to delete the contents of or set the pointer to null. Now, this program I'm showing is actually broken, because after we've transferred the permission, we should not be able to set the pointer to null, because that could, again, be a data race, right? And so here, the cool thing is that we get to rely on Rust borrow checker to check our proof. So this is some high-level, more complex proof, and access permissions, which is kind of a separation logic inspired, for those of you familiar. But we have this nice interface that is given us by the fact that we are relying on the Rust type checker. OK, so, and this is why we have this proof mode, which is this program, this style of code that is borrow checked but isn't then compiled. And all of those are all the fragments that are in fact proof mode here. And as a reminder, those are ghosts. They go away. So we're not spending any runtime resources on transferring this permission. And the alternative here would be at runtime, we transfer an owned box elsewhere, but that wouldn't require a channel, and then that transfer explicitly. Here, if we can set up a protocol around this to control how this permission is transferred correctly, abstractly, then we get to do it without any runtime cost. OK, so generally speaking, we're designing Verus as a pragmatic toolbox for verification. We've seen that we want to encode it to SMT queries efficiently, so we get good verification performance. We have support for things other than Z3 and separate Z3 modes to reason about specific things that come up a lot in system software, like nonlinear arithmetic and bit vector. And also, we've been working on shared memory concurrency support. So if you want to reason about a concurrent programs, we have techniques to do that. And this is based primarily on work done at CMU by Travis Sanz and other folks. And what I wanted to showcase here is how does it look like if you want to use a different prover. Here we're going to try to prove some property that if we divide x by y, then the result is smaller. We get to use the nonlinear arith prover to do that, which is geared towards exactly that goal, is hopefully more efficient. And then we can do bit vector arithmetic and do verification using that. And this sidestep the issue that the Z3 is sometimes not great at doing all of this reasoning if it's mixed together. So it allows us to be very specific. OK, so again, around Verus as a pragmatic toolbox verification, as researchers, we want to scale up verification to real-world systems so that people can benefit from these techniques. the cost is still high, but we believe we're bringing the cost down as a community. And so it's starting to make sense in the industry to verify some systems, some kind of high value systems. And hopefully that will continue, the cost will continue to go down so that more people can use tools like this. But as researchers, we want to prove that Verus works or is usable at some level. And so we have been working on, and folks in different institutions have been working on different projects around using Verus to verify different things. So there's a project verifying the correctness of Kubernetes controllers. There's a project led by Matthias, who's in the room, on verifying the page table code for an operating system kernel, and more in general, how to verify an operating system with techniques like this. And there's more that we're working on, and it's to come from a bunch of institutions. So very quickly, I mentioned that we're using just unmodified Rust mostly, but we have this situation in which we have this ghost code that we want to appear in the source, but we want to make disappear before it makes to the compiler. Rust really doesn't understand this, because why would it? Why would you want to write code that doesn't appear in the binary? And so we have been working with a bunch of folks in the community, folks at ETH from Prusty and Xavier, working on Crusoe, which is another verification tool, to add support for ghost code to the Rust compiler. And we'll be making some progress here. Great. So talked about Verus. Verus is our toolbox for system verification. All of these people on the slides have worked on Verus, and these people are not in any specific order. So Verus is an open source project which spans a bunch of different institutions. I want to highlight, because we are at ETH, that the first few tens of thousands of lines maybe were written by Chris Oblitzer, Microsoft, and me while I was at ETH. So I want to acknowledge ETH for that. But a lot of these people have had input even early on the design of the tool. So if you're interested, try the guide. Try Verus. We have this, thanks to folks at CMU, we have this cool Rustlang, play Rustlang alike over there. There's a paper if you're academically minded. And if you have questions, you're trying the tool, things don't work, get in touch, either on GitHub, just open an issue, or shoot me an email. And yeah, I think with that, I'm done. Yeah.
Thanks for the talk. I was really curious about this P pointer thing. So you know about Ghost Cell?
Yes.
So is this more general? I'm trying to understand. Is this because you can transfer the permissions in the proof? Is this the idea?
Right. So Ghost Cell is the branded lifetime, right? Nice. So Ghost Cell, let me say this correctly, hopefully. So Ghost Cell has this technique where the permission is encoded as a branded lifetime, essentially, and then you move around the permission. And that's mainly encoded just in the Rust type system. That means that you don't get to use the tool's reasoning to determine how you can move around the permission. So using this, be vague, I'm happy to be more precise later, but with Verus we get to, so things like PPTR put has preconditions that are checked by the SMT solver. So we get a lot more flexibility on how we transfer the permissions. We can combine permissions into like a linear hash set, for example, like linear ghost hash set, and then you get them out when you need them, things like this. So we get to rely on the SMT solver in addition to having the syntactic element that kind of proves your ownership. Yeah.
Thanks.
Yep. Good question. Yep. And Ralph, correct me if I'm wrong.
I don't have a question, but it's a comment. Oh, okay.
To add to that, the one way to think about it is the hard part with separating the permissions from the data is to still know which permission is for which data, which Ghost Cell does with this branded lifetime trick, which is super tricky and unergonomic and everything, but the amazing thing, it works in the Rust compiler without anything extra. Verus doesn't have the need for any such crazy hacks because they can just use all the extra machinery they have for reasoning about values and like all the SMT support to do that reasoning, and then you don't need the brands and stuff. So it becomes a lot simpler.
Yep. Thank you.
My question is about practicality. So let's say in the practicality spectrum of which kind of programs can you verify with that? For example, can you verify like sorting algorithms?
Yeah.
Which I think, there are lots of even newer algorithms that are more optimized or whatever, but are they correct?
Yeah. Sorry, is there more to the question? Great. Great question. So yeah, you can verify things like algorithms. In fact, the state of the art is pretty good at verifying individual algorithms, especially if they don't have side effects. So if they're kind of this is not a sorting algorithm. I think we have a sorting algorithm example somewhere, but I just had this. This is just reversing of an array, which is much simpler. But you can imagine that this gets more complicated when you try and think about sorting algorithms. Sorting algorithms, because they don't, have usually concurrency and have less communication with the rest of the complexity of the system, are something that a lot of tools do fairly well at this point and very quickly, and we can do as well. The state of the art is multiple thousands of lines of programs. The largest projects I know of are, one of ours in Daphne was very better KV, which is a verified key value store, which I think is about 5,000 lines of source. There's projects in using the cog prover. I think Daisy NFS is one of them, is a file system, which is a verified file system. Completely different technique, but I think of a maybe comparable scale. And I know that there is a Wave, which is a verified, it's not fully, it's not full functional correctness. So Wave is a runtime for WebAssembly, and they don't verify, my understanding is they don't verify that it runs WebAssembly correctly, but they do verify that the runtime will not do anything that it's not supposed to. So WebAssembly is supposed to be, sandboxed, and so they verify the sandboxing property. And so the scale we are at now is multiple thousands of lines of code, multiple, PhD years of effort. That's hopefully where we are trying to improve on. So, in fact, the verified page table project thing was successful in that sense because we got very good verification time, so the iteration time was good. You can ask Matthias how frustrating it was afterwards. And it's a sizable program with very complex interaction with the system. So, page table is writing to the page table memory or whatever. Good question. And if you gotta catch a train, feel free to run.
Yeah, it's 9:05.
How does this interact with memory allocation or memory allocation failure?
That's a great question. We currently assume that allocation is not going to fail. And we could have a separate API that does not make that assumption. The advantage of allocation failure is that in Rust regularly, I think it just crashes, which is not ideal for a verified program, but not the worst outcome because you're not going to do anything horribly wrong. One interesting thing about at least these kind of techniques is you're still proving partial correctness anyway, which means you're not going to actually prove that the program will terminate. So a program can just also spin forever and be considered correct. There are techniques to also address that. So there are limits, but for sure, allocation is something that currently we assume to always succeed. And if we want complete soundness from that aspect, we should probably also check every allocation and assume that I can handle, and the user would have to handle the case of the panic. In practice, many systems just make that assumption anyways, and it's a pragmatic choice. But for some environments, you would need something else. Does that answer the question? Yeah, thank you.
Remember to put the mic close, and I think after that we'll do an interview.
All right. You said that you support some kind of concurrency primitives. in the language, so you're able to reason about concurrent programming.
Yeah.
So you can do stuff like prove non-existence of deadlocking.
So, great question. Non-existence of deadlocking is what people call liveness usually, and liveness is hard. Turns out there are techniques that are being developed that are making that general kind of understanding of liveness maybe not as true anymore. We focus on correctness, so the concurrent program results in the correct produces the correct result, and there are no data races, there are no concurrency hazards. So we're focusing on that aspect, and a verified program in Verus using the concurrency verification techniques could very well still be deadlock otherwise. Great question.
All right. Any more questions?
So far, examples that I saw, they seem like to verify within a body of the function if things are. What about across the calls, like in the continuation style, or you sometimes execute a bit, then the data goes somewhere else, come back, and you continue, and you would like to verify that the whole flow is correct.
Right.
And yeah.
Yeah, great question. So if it's just a regular function call, like we were doing for I think here, the transfer function, what happens is that we do this module verification approach where you talk about what the transfer function does, and then that lets you thread that knowledge through the transfer function call. I think you're also asking things about like a continuation passing style or like async, essentially. And we haven't looked into async yet. We think a lot of the techniques may transfer fairly well, at least the non-concurrency reasoning ones. I'm not going to make any statements about concurrency. But generally speaking, this style of tools requires you to build up your verification using this module style. So every function will carry a specification that says what it does abstractly, and you can abstract quite a bit, fortunately. And then if you have big programs and complex programs, the technique that Verus optimizes for is a state machine refinement, which is using the kind of iron plate style, if you know what that is, and which means that you essentially have this very high level description of what the program does. So for example, a key value store is just a map from keys to values, and then the transition you can have is just insert a new key, read a key, for example, and then you progressively refine and write proofs that those relationships are preserved down to a level where you have all of the operations. So all operations might be perform this read on disk, get the result of this read from disk, and all of these map to some high level operation. And that's the style that the Iron Fleet style uses. There are different techniques, but transition systems and TLA style systems are fairly common for throwing some keywords for you.
Turns out these keywords are also in the online questions. So,
Mm-hmm.
Gary? Thank you. So, to the online questions. One is, are you aware of quantitative type theory, and what do you think of this application? Or is it not relevant in your case?
I don't remember what quantitative type theory is.
Me neither. Just
So
reading
does somebody
stuff.
know? Yeah.
It's the type system used by Idris, where each value is annotated by how often it can be used, either 0, 1, or unannotated means undefined.
Great. So I think that's an extension of a linear type system. Like it's a linear type system with more flexibility.
It supports both irrelevant and linear types, yes.
Yeah, great. So let's see. I don't know. I think there's an interesting answer here, but it may be long. Whoever asked this, please get in touch. So let's see if I can make it quick. So linear types, we think is a very convenient interface for the kind of style proofs we're writing, but there's been a lot of success using separation logic, which is a style of type system in which the values can be used multiple times in certain ways. So you get to take a value, split it up, and then give fractions to everybody. So there's definitely overlap there. Our techniques are very much inspired by those. The relationship with Iris, I really don't remember much of Iris. I looked at it at some point, so I'm not sure. But yeah, if you're interested in more, just get in touch. Hopefully that's satisfying enough.
Mm-hmm. And a final question, can you handle string-like things?
Yes. Not a lot so far, but we do have a basic support for strings where you get to use string literals and you get to concatenate strings and do some string operations and then kind of prove that those result in certain things. We're, I think, lacking a little bit in the parsing and currently lacking in at least for string in like parsing a string and determining that the value, the integer you get corresponds to the string value. Yeah.
Cool. I think that will conclude the questions. A big round of applause, please.
Thanks a lot for the questions.